The most powerful storm on Earth right now is not in the Atlantic. It is not approaching Florida or grinding through the Caribbean. It is churning through the western Pacific Ocean with its eye locked directly on American soil. Super Typhoon Bavi, a Category 5 monster carrying sustained winds exceeding 175 miles per hour, is bearing down on Guam and the northern Mariana Islands. And the part that makes this situation genuinely terrifying is not the storm itself. It is what came before it. These islands are still in ruins from the last super typhoon that hit them 3 months ago. Back to back. 2 catastrophic storms. Same tiny islands, same year. The second potentially stronger than the first. This is the worst case scenario that emergency planners use as a theoretical example in training exercises. In July 2026, it is not theoretical. Let us build the complete picture of what Bavi is, how it became what it became, what these islands are experiencing right now, and what the science says about why storms like this are becoming impossible to ignore. Bavi started as something that barely warranted attention. In late June 2026, meteorologists were tracking a disorganized cluster of tropical convection east of the Philippines. On July 2nd, the Joint Typhoon Warning Center based in Hawaii was monitoring it as System 9, a loosely organized area of disturbed weather that had not yet achieved the organized structure required for tropical storm designation. It was not on most people's radar. It was barely on the professional forecasters' radar in the sense of demanding urgent attention. That changed with a speed that makes this storm scientifically remarkable. By July 3rd, the Joint Typhoon Warning Center had designated it Tropical Storm Bavi and was already flagging it for rapid intensification. The storm was moving west-northwest at approximately 12 miles per hour, steered by a subtropical ridge positioned to its northeast. And the conditions lying ahead of it in its projected path were almost perfectly engineered to transform a modest tropical storm into something catastrophic. Exceptionally warm ocean water extending well below the surface, low wind shear throughout the atmosphere, high humidity from the ocean surface up through the mid-levels of the troposphere. The 3 ingredients that a tropical cyclone needs to explode in intensity were all present simultaneously. By July 4th, Bavi had reached Category 5 status. Maximum sustained winds of 165 miles per hour with gusts considerably higher. The eye, approximately 21 miles in diameter, had become well-defined and symmetric as the storm's central dense overcast grew more organized and cloud-top temperatures plunged. Satellite imagery showed the kind of classic textbook super typhoon structure that atmospheric scientists recognize immediately as the signature of a storm that has found its groove and is extracting energy from the ocean at maximum efficiency. Yale Climate Connections meteorologists Jeff Masters and Bob Henson described a system that appeared capable of becoming a dangerous Category 4 or Category 5 super typhoon within 24 hours of its first advisories. What actually happened was faster than that prediction. Bavi went from a disorganized tropical storm to a Category 5 super typhoon in approximately 48 hours. This is the definition of rapid intensification, a phrase that has become increasingly common in the scientific literature on tropical cyclones, and increasingly alarming to emergency managers who depend on lead time to move people to safety. June 2026 was the second warmest June globally on record according to the Copernicus Climate Change Service. The global average surface temperature that month sat 1.39 degrees Celsius above pre-industrial levels. The exceptionally warm ocean surface temperatures in the western Pacific that Bavi was crossing were a direct contributing factor to how explosively the storm developed. The ocean was simply providing more energy than a storm of its size would typically encounter, and it consumed that energy with terrifying efficiency. Now here is the context that transforms this from a dramatic weather event into a humanitarian catastrophe. On April 14, 2026, Super Typhoon Sinlaku made direct landfall over the northern Mariana Islands, with its large eye passing over both Tinian and Saipan simultaneously. At its peak, Sinlaku carried sustained winds of 185 miles per hour and a central pressure as low as 890 millibars, placing it among the strongest typhoons ever recorded in the western Pacific in terms of intensity. Its movement at landfall was brutally slow, which meant it subjected the islands to an extended battering rather than a rapid passage. The storm dumped over 20 inches of rain on parts of the islands. Power infrastructure was knocked out across large portions of Tinian and Saipan. Catastrophic structural damage occurred throughout the region. Totals. Estimated damage was placed at approximately $1.5 billion. 6 people died, including members of a vessel crew that capsized near Pagan Island during the storm. When Bavi began organizing in early July, parts of Tinian and Saipan were still without electricity. 2.5 months after Sinlaku, the power grid had not been fully restored. Emergency shelters were still housing displaced residents. Homes with tarps over damaged roof structures instead of intact roofing, infrastructure compromised across the islands. And now bearing down on these same communities in the same year was a second Category 5 storm predicted at that point to potentially be even more powerful than the storm they were still recovering from. NPR reported that as Bobby approached, shelters on the islands were packed and turning people away. An emergency official in Guam told reporters that there were many vulnerable communities across northern Guam, people living in substandard building materials, and that from what was being heard from Saipan and Tinian, the situation was dire. The National Weather Service used explicit language in its public communications. This is an extremely dangerous and life-threatening situation. A government official in Guam said publicly that they aimed for 0 fatalities, expressing hope, but acknowledging it was going to be a rough night and a rough day. The Port Authority of Guam suspended operations entirely. Andersen Air Force Base on Guam, one of the most strategically significant American military installations in the Pacific, asked all non-essential personnel to shelter in place. These are not routine precautions. These are the actions of emergency systems confronting a threat they are taking with complete seriousness. The uncertainty in the days before Bobby made landfall created significant anxiety for emergency managers across all 4 affected islands. The central operational question was which communities would take the direct hit from the eye wall. The American GFS computer model placed the center tracking directly over Tinian and Saipan, the same 2 islands already devastated by Sinlaku in April. The European ECMWF model tracked Bobby slightly further south, placing the center closer to Rota and Guam. The difference between those 2 scenarios is the difference between communities taking a catastrophic eye wall passage and communities experiencing severe but potentially survivable typhoon force conditions. Both scenarios were deeply concerning. The only question was which community would absorb the worst of it. What actually happened was that Bobby's center passed over Rota on the morning of July 6th local time. Rota, an island of approximately 2,000 people, the southernmost island of the Northern Mariana Chain, located about 40 miles northeast of Guam, took the eye wall directly. Winds on Rota exceeded 150 miles per hour as the eye passed overhead. Local authorities reported major and widespread damage. Communications were severely disrupted immediately following the storm's passage, making initial damage assessment difficult. Guam, roughly 50 miles to the southwest of Rota, experienced maximum sustained wind gusts of 111 miles per hour. Saipan also recorded gusts of 111 miles per hour. Guam set a new daily rainfall record at its international airport, 12.5 inches of rain in a single day. In some locations, rainfall totals approached 18 inches, depending on proximity to the eye wall. Let us put hard numbers around what those measurements mean, because the phrases Category 5 and Super Typhoon can begin to feel abstract without context. Hurricane force winds are defined as sustained winds of 74 miles per hour or higher. A Category 5 hurricane or typhoon requires sustained winds of 157 miles per hour by definition. Bobby at peak intensity was carrying maximum sustained winds of 175 miles per hour, comfortably into Category 5 territory and sitting near the top of the scale. The storm's central pressure dropped dramatically during its rapid intensification phase, with computer model guidance projecting central pressure as low as 910 millibars as it approached the islands. For scale, the strongest typhoon ever recorded in history, Typhoon Tip in 1979, had a central pressure of 870 millibars. Sinlaku in April 2026 had touched 890 millibars. Bobby at 910 millibars was operating in the same tier of historically extreme storms. Satellite imagery from the Copernicus Sentinel-3 satellite captured on July the 6th showed the eye of Bobby positioned close to Rota, with winds at the island exceeding 240 kilometers per hour. The storm's dense cloud bands completely obscured Guam, Tinian, and Saipan from the satellite view at the moment of image acquisition. And through all of that, as of the time reporting was available, no deaths had been confirmed on Guam or the Northern Mariana Islands. Take a moment with that outcome. A storm with sustained winds exceeding 150 miles per hour passed directly over an island of 2,000 people. Major structural damage was widespread. Infrastructure was hit hard. Communications were disrupted for an extended period. And the communities came through without confirmed fatalities. This is not luck. This is preparation operating exactly as it is supposed to operate. Emergency officials had been issuing warnings days before Bobby arrived. Evacuation orders went out with sufficient lead time for people to act. Emergency shelters were opened across the islands, even when they filled beyond their designed capacity. Port operations were suspended. Military installations went to full preparation posture. The public messaging was honest, specific, and urgent. People were told clearly and repeatedly that they needed to be in their safe location before conditions deteriorated, that movement outside during the eye wall passage would be life-threatening, and that the approach of extreme winds should be treated with the same urgency as a tornado bearing down on a specific location. That communication, combined with communities that have unfortunately been through enough typhoon events to understand what taking a warning seriously looks like in practice, is why the Northern Mariana Islands and Guam survived Bave without adding to the death toll. The lesson embedded in that outcome is the same lesson that Japan teaches the world with every major earthquake and tsunami. The storm's intensity is the product of nature and atmospheric physics. The survival rate is a human choice made in the hours and days before the storm arrives. After passing over the Mariana Islands, Bave did not dissipate. The Western Pacific provided warm water across enormous stretches of open ocean ahead of the storm's track, and Bave was moving through an environment that allowed it to maintain extreme strength well past the Marianas, moving westward at approximately 9 miles per hour into the Philippine Sea, still carrying sustained winds exceeding 150 miles per hour. The storm's next destination became the primary concern for meteorological and emergency agencies throughout the region. The forecast consensus, as reporting became available, was that Bave would gradually weaken as it moved westward and eventually northwestward, encountering slightly cooler waters and potentially increasing wind shear. But the storm was expected to remain a powerful typhoon, equivalent to a Category 2 hurricane or stronger, as it approached Taiwan. Landfall in Taiwan was being projected for approximately July 11th, with the storm then continuing into mainland China. Even at reduced intensity from its Category 5 peak, Bavai approaching Taiwan represents a serious and multidimensional threat. Taiwan's mountainous terrain causes what meteorologists call orographic enhancement, rainfall dramatically amplified as the storm is forced upward over mountain ranges. Flash flooding and landslides become major risks, even when sustained winds have dropped well below super typhoon levels. After Taiwan, Bave was expected to continue into parts of southern or southeastern China, bringing flash flooding and additional wind impacts to a significant stretch of coastline. Now let us address the bigger question that Bave and Sinlaku together demand. 2 Category 5 storms hitting the same islands in the same year. Is this normal? Is this getting worse? And what is actually driving the intensity of events like these? The answer requires precision because this is a topic where oversimplification in either direction produces a distorted picture. The total number of tropical cyclones globally has not dramatically increased compared to historical records. What has changed, and what the data consistently shows, is that the strongest storms, Category 4 and Category 5 intensity, are becoming a higher proportion of all storms that form. The storms that do reach major intensity are reaching it faster, holding it longer, and in some cases, achieving it closer to populated coastlines than historical patterns would have predicted. The mechanism is straightforward atmospheric physics. Tropical cyclones are heat engines powered by warm ocean water. Warmer water provides more energy. More energy means stronger potential intensity. Ocean temperatures in the Western Pacific, the most active typhoon basin on Earth, have been running above historical averages, consistent with a broader pattern of ocean warming. June 2026 being the second warmest June globally on record, as confirmed by the Copernicus Climate Change Service, is part of that broader trend rather than an anomaly isolated from it. Rapid intensification, the phenomenon that turned Bave from a disorganized tropical storm to a Category 5 in approximately 48 hours, is the aspect of this pattern most concerning from an emergency management perspective. The reason is the compression of preparation time. If a storm gradually builds over 5 or 6 days to Category 5 strength, emergency managers have 5 or 6 days of progressively urgent lead time to communicate warnings, execute evacuations, and move vulnerable populations to safety. If a storm goes from a tropical storm to Category 5 in 48 hours while still 600 miles from the coast, that preparation window shrinks dramatically. The warning time that communities depend on is compressed precisely as the threat level escalates most rapidly. For the specific case of Bave, the rapid intensification was caught early enough by the forecasting community that the Mariana Islands had several days of warning. The National Weather Service, the Joint Typhoon Warning Center, and local emergency managers all performed their functions effectively. That lead time is the proximate reason that 0 fatalities resulted from a Category 5 eye wall passage over an island of 2,000 people. But the Western Pacific Islands face a structural vulnerability that goes beyond the question of any individual storm. They are tiny, they have small populations. They have limited infrastructure to begin with, infrastructure that sits in the direct path of the most intense tropical cyclone basin on Earth. And they now face a pattern in which 2 Category 5 or near Category 5 storms have hit the same geography in the same year, leaving almost no interval between them for meaningful recovery. When Sinlaku knocked out power to Tinian and Saipan in April, and Bave arrived in July with those communities still operating on compromised grid infrastructure, the compounding effect extends far beyond what the damage numbers capture individually. It is double the damage to infrastructure that was already weakened, plus the psychological and economic burden on communities that had not had the opportunity to recover plus the logistical challenge of attracting reconstruction resources to the same location twice in the same calendar year. Federal disaster declarations for Sinlaku were still being processed when Bavi formed. FEMA resources committed to Sinlaku recovery were still deployed when Bavi arrived. The question of how American Pacific Island territories rebuild and strengthen their resilience against this pattern of intensifying storms is not purely a meteorological question. It is a policy question, an infrastructure investment question, and ultimately a question about what level of federal commitment these communities can realistically expect. To understand why rapid intensification like what Bavi demonstrated matters scientifically and operationally, the atmospheric conditions that enable it deserve specific attention. 3 conditions must align simultaneously for rapid intensification to occur. First, ocean temperature. The ocean needs to be warm not just at the surface, but through the upper layers, because a powerful storm churns up deeper water as it moves forward. If that deeper water is cold, it cools the surface temperature beneath the eye and cuts off the storm's energy supply. The Western Pacific in July 2026 had anomalously warm temperatures extending well below the surface, providing essentially unlimited fuel for Bavi's intensification engine. Second, wind shear. The change in wind speed and direction with altitude needs to be low. High wind shear tears apart the organized structure of a developing tropical cyclone, preventing the towering thunderstorm clusters around the eye from establishing and maintaining themselves. Bavi moved through an environment of low wind shear in its early development phase, allowing it to build without atmospheric interference. Third, upper-level outflow. The storm needs an efficient pathway for the warm, moist air that has risen through its thunderstorm towers to exhaust at high altitude. Forecasters noted that developing upper-level outflow enhanced by atmospheric conditions near Japan was actively supporting Bavi's ability to intensify as it approached the Marianas. All 3 conditions aligned simultaneously over a 48-hour period. The result was one of the faster intensification events seen in the Western Pacific in recent years, and it produced a storm that was significantly stronger at landfall than many residents had time to fully, mentally reconcile with, even with days of advance warning. The psychological challenge of processing a forecast that says this storm will be dramatically stronger in 24 hours than the models were showing yesterday is real and significant. It requires a level of trust in the forecasting process that needs to be built over time and reinforced through every storm event. The broader meteorological picture surrounding Bavi in early July 2026 adds another layer of context. A second tropical system, separate from and much less intense than Bavi, was simultaneously tracking from the Philippines toward coastal China. Expected to remain at tropical storm level, this secondary system was projected to bring 100 to 200 millimeters of rain to parts of China's coast before dissipating. Significant flash flooding risk for low-lying coastal areas even without reaching typhoon intensity. Japan's Kyushu, Shikoku, and central Honshu were expecting rainfall totals exceeding 100 millimeters over a 3-day period from atmospheric moisture associated with Western Pacific activity. Parts of India, Thailand, Vietnam, Laos, Bangladesh, and Myanmar were experiencing active monsoon rainfall simultaneously, not directly connected to Bavi, but part of the same broader pattern of moisture-laden atmospheric systems that characterized early July 2026 across the entire Indo-Pacific region. The Bay of Bengal was being monitored for potential tropical development in the days following Bavi's landfall, representing an additional area of concern for Bangladesh, India, and Myanmar that was developing independently of the Western Pacific activity. The Western Pacific typhoon season by early July 2026 had already produced 7 tropical cyclones, with the season tracking as an active one, consistent with elevated sea surface temperatures and a neutral to weak La Niña pattern that historically favors increased Western Pacific typhoon activity. August, September, and October historically bring the highest frequency of intense storms in the basin. The 2026 season was demonstrating well before its statistical peak that it was not going to be quiet. For anyone living in or planning to be in typhoon-prone regions of the Western Pacific, the operational lessons from Bavi are specific, practical, and worth stating clearly. Early warnings exist for a reason that has been demonstrated with uncomfortable clarity by the Mariana Islands outcome. The National Weather Service, Joint Typhoon Warning Center, and local meteorology agencies issue typhoon warnings days in advance specifically so that communities have the time needed to act on them. The warning is not information for after the storm arrives. It is a window that closes when conditions deteriorate to the point where movement outside becomes dangerous. Once typhoon-force winds arrive, that window has closed. Acting during the warning period, not when the outer rain bands start appearing, is the decision that determines outcomes. Evacuation centers are not a last resort. They are the primary tool. In Guam and the Northern Marianas, the fact that shelters were at and beyond capacity before Bavi made landfall is the direct mechanism behind the 0 fatality outcome. People who live in vulnerable structures, older buildings, homes with already damaged roofing from Sinlaku, properties in low-lying coastal areas susceptible to storm surge, made the decision to move before conditions made movement impossible. Storm surge awareness is as critical as wind awareness and consistently underweighted in how people think about typhoon risk. Historical data from major tropical cyclones globally shows that storm surge, the abnormal rise in sea level driven by a storm's winds pushing water toward shore, accounts for the majority of deaths in tropical cyclone events worldwide. A Category 5 typhoon approaching a low-lying coastal area can produce storm surge of 20 feet or more in extreme cases. That wall of water moving inland is not survivable in most conventional structures in its direct path. Wind speeds produce the dramatic footage and the headline numbers. Storm surge kills the people who are not already in elevated reinforced shelter when it arrives. Communication planning before a storm's arrival matters in ways that become obvious only after communications are disrupted by the storm itself. Rhoda lost contact with the outside world for a significant period following the eye wall passage, making initial damage assessment difficult and delaying the organization of external assistance. Having a pre-established plan for where family members will shelter, how contact will be made after the storm, and where assistance should be directed reduces both the panic during the community's communication blackout and the inefficiency of emergency response, trying to identify where people are and what they need. Super Typhoon Bavi came screaming out of the Western Pacific in early July 2026 as potentially the strongest storm on Earth at that moment. It hit communities already broken by Sinlaku 3 months earlier. It delivered sustained winds exceeding 175 miles per hour at its peak. It dumped record rainfall on Guam. It passed a direct eye wall over the island of Rota with winds exceeding 150 miles per hour. And it produced 0 confirmed deaths on Guam and the Northern Mariana Islands. That outcome is not a miracle. It is not coincidence. It is what happens when warnings are issued with adequate lead time, when communities take those warnings seriously enough to act decisively, when emergency systems function as they are designed to function, and when people move to safety before conditions make movement impossible. After everything those islands have absorbed in 2026, Sinlaku in April with its $1.5 billion damage toll and 6 deaths, followed by more than 2 months without full power on Tinian and Saipan, followed by Bavi arriving before recovery was complete. The 0 fatality outcome from Bavi represents a testament to what preparation and community response can achieve against even the most intense natural forces the Western Pacific can generate. The storm is now tracking toward Taiwan and China, diminished from its Category 5 peak, but still carrying significant destructive potential. The 2026 Western Pacific typhoon season has months of statistical peak activity still ahead of it. More storms will form, more warnings will be issued, more communities will face the decision of whether to act early or wait to see how bad it gets. The answer that Guam and the Northern Mariana Islands just demonstrated, without any ambiguity, is that acting early is the decision that keeps people alive. The strongest storm on Earth this week passed over American soil and killed nobody. That sentence should be remarkable. It should also be a reminder, permanent and specific, that the science gives us the warning and the choice of what to do with it is always human.